Forecasting is a fundamental component of demand management and supply chain planning, even though organizations should use actual sales or demand data whenever available. Modern supply chains increasingly rely on real-time demand signals, lean practices, and make-to-order strategies to reduce dependence on forecasts. However, forecasting remains essential whenever decisions must be made before actual demand information becomes available, particularly for products with long lead times or complex supply networks. Forecasts support inventory planning, procurement, production scheduling, transportation capacity, and logistics resource allocation. Because future demand is uncertain, forecasts provide an informed estimate rather than a guarantee. Logistics professionals must understand forecasting principles, limitations, and applications to make effective planning decisions. A key principle in forecasting is recognizing the uncertain nature of the future. Forecasts are inherently imperfect because customer behavior, market conditions, competitive actions, and economic factors constantly change. As a result, forecasts often contain variability, bias, and error. Aggregate forecasts for product families are generally more reliable than forecasts for individual items because variations tend to offset one another. Likewise, shorter-term forecasts are usually more accurate than long-term projections because uncertainty increases over time. Effective forecasters acknowledge these limitations and communicate forecast assumptions and error ranges. Organizations improve forecasting quality by using reliable demand data, incorporating market intelligence, and continuously evaluating forecast performance against actual outcomes. Visualizing demand data is an important early step in the forecasting process. Graphs and charts help identify trends, seasonality, business cycles, and random variations that may not be obvious in numerical data alone. Through visualization, forecasters can detect recurring patterns such as peak demand periods, growth trends, or declining product popularity. Strong seasonal patterns often require special treatment because forecasting directly from raw data may produce misleading results. Visual analysis supports better model selection and provides valuable insights for decision makers. It also helps logistics professionals understand how customer demand behaves over time, enabling more accurate planning of transportation, warehousing, labor, and inventory resources throughout the supply chain. The forecasting process follows a structured sequence of activities designed to improve forecast reliability. After collecting and validating historical data, forecasters analyze patterns and determine whether seasonality exists. If significant seasonality is present, data are often deseasonalized before applying forecasting models. This removes recurring fluctuations and allows underlying demand patterns to be analyzed more effectively. Once a forecast is generated, seasonal factors are reapplied through reseasonalization to produce realistic future demand estimates. Forecasts are then reviewed, adjusted where necessary, and incorporated into sales and operations planning processes. Continuous monitoring and refinement ensure that forecasting models remain relevant as market conditions, customer behavior, and operational requirements evolve over time. Selecting the most appropriate forecasting method depends on forecast objectives, data availability, product characteristics, and market stability. Forecasting methods are generally categorized as qualitative or quantitative. Qualitative methods rely on expert judgment and are useful when historical data are limited, unavailable, or no longer relevant. Common examples include executive judgment, sales force estimates, market research, and the Delphi method. The Delphi technique gathers anonymous expert opinions through multiple rounds to achieve consensus while minimizing bias and groupthink. These approaches are especially valuable for new products, emerging markets, strategic planning, and situations where rapid environmental changes reduce the usefulness of historical demand patterns. Quantitative forecasting methods use mathematical analysis of historical data and relationships among variables. Time series forecasting assumes that past demand patterns will continue into the future and includes methods such as moving averages, weighted moving averages, and exponential smoothing. Exponential smoothing is particularly popular because it balances recent demand information with previous forecast values while filtering random fluctuations. When historical patterns are insufficient, associative or causal forecasting techniques can be applied. These methods use external variables that influence demand, such as housing starts, economic indicators, or demographic changes. Regression analysis is one of the most widely used causal forecasting tools because it quantifies relationships between demand and measurable influencing factors. Forecasting approaches must also consider distribution channels and forecast accuracy measurement. Different channels, including retail, wholesale, direct-to-consumer, business-to-business, and omni-channel networks, often exhibit distinct demand patterns, service expectations, and replenishment requirements. Consequently, separate forecasting approaches may be required for each channel. Once forecasts are generated, organizations evaluate reliability through forecast error measurements such as forecast accuracy, mean absolute deviation, MAD, mean squared error, MSE, mean absolute percentage error, MAPE, and tracking signals. These metrics help identify model weaknesses, monitor performance, and support continuous improvement. Understanding forecast accuracy enables logistics professionals to determine appropriate safety stock levels, capacity requirements, and risk mitigation strategies while maintaining desired customer service levels.